Look at this image. At first, it seems like digital noise, a pale cloud scattered with tiny points. But those points are not pixels. They are stars. More than 60 million of them, compressed into one view of the crowded heart of the Milky Way. The image is so large that you could keep zooming for hours and still find new clusters, dark clouds, and isolated suns. And the telescope that captured all of this was never built to study this part of the sky. Our galaxy is a spiral more than 100,000 light-years across. Earth sits in one of its arms, roughly halfway from the center, and our solar system needs about 240 million years to complete a single orbit. When we look toward the bright band of the Milky Way, we are looking through the disk from inside it. That creates a problem. Stars overlap along the same line of sight. Clouds of gas and dust block or red invisible light. And near the galactic bulge, the number of stars becomes so extreme that several sources can blur into what looks like one. The center is there for both a treasure and a trap. It contains an enormous population of stars and planets, but separating them requires unusual sharpness, sensitivity, and a very wide field of view. Most telescopes can deliver two of those qualities. Euclid can combine all three. Euclid is a European Space Agency mission with contributions from NASA. It launched in July 2023 and began routine science observations the following February. Its primary job is not to map our galaxy. Over 6 years, Euclid is measuring the shapes, distances, and motions of billions of galaxies out to about 10 billion light-years. Scientists use those measurements to trace how dark matter structures the cosmos and how dark energy influences its expansion. Euclid normally looks away from the dense plane of the Milky Way, where dust and crowded stars complicate the survey. But astronomers realized that the same visible light camera designed to measure distant galaxies had exactly the combination needed for the galactic bulge. So they made a special request. For roughly one day, the Dark Universe telescope stopped looking outward and turned toward the light of our own crowded center. The observation took place on March 23, 2025. Euclid's visible light camera collected 9 adjoining pointings over about 26 hours. Each pointing covered a patch of sky larger than the full moon. When the 9 pieces were assembled, they produced a 6-gigapixel mosaic. Euclid's sharpness and sensitivity are comparable to Hubble's wide-field camera, but the area covered in one Euclid pointing is about 270 times larger. That changes the economics of observing time. ESA estimates that the Keck Observatory would need roughly 2,000 hours to cover the same mosaic from the ground. Euclid did it in a little more than a day. Its position in space also removes atmospheric blur, while the wide detector records faint stars across a huge area at once. The result is not simply a large photograph. It is a precisely measured catalog in which individual sources have positions. And once a position is measured at one moment, a later observation can turn that position into motion. The public image rewards almost any level of zoom. One region contains a tightly packed star cluster. Another is crossed by a dark molecular cloud. Elsewhere, glowing nebulae sit in front of layers of stars that would merge together in a less precise image. Euclid's visible camera recorded the original data in black and white. For the public release, scientists added color information from the ground-based Canada-France-Hawaii telescope. The color helps structures stand apart, but the scientific power comes from separation. Euclid can identify individual stars in a field that otherwise becomes luminous fog. The mosaic includes 51 known planetary systems. It also contains brown dwarfs, binary stars, stellar motions, and dust structures that researchers can study long after the image release. This is why a photograph made in 26 hours can support many different investigations for years. The most important use of this image begins with an alignment that has not happened yet. Imagine a distant source star. Between that star and Earth, a second star passes close to our line of sight. According to general relativity, the foreground star's gravity bends the background light. From Earth, the source briefly appears brighter. This is gravitational microlensing. Now place a planet around the foreground star. The planet adds its own small gravitational distortion. In the recorded light curve, a broad brightening develops a smaller bump or asymmetry. The planet does not need to emit light. It does not need to cross the face of its star. Its gravity gives it away. The exact shape and timing of that disturbance contain information about the planet and the geometry of the event. But the alignment is temporary and cannot simply be repeated. A telescope has to be watching the right crowded field at the right time. That is why astronomers aim microlensing surveys toward the galactic center, where millions of possible source stars sit behind millions of possible lenses. More stars create more chances for a rare alignment, but they also make the field harder to resolve. Euclid's image attacks both sides of that problem. Most familiar planet searches favor worlds that are easier to detect repeatedly. The transit method waits for a planet to pass in front of its star. Radial velocity measurements look for the star's regular gravitational wobble. Both methods are extraordinarily productive, but their strongest signals often come from large planets on relatively short orbits. Microlensing samples a different population. It can reveal cold planets far from their stars, and it can detect systems whose geometry never produces a transit from Earth. Over the last 20 years, almost 300 exoplanets have been discovered through microlensing, all with ground-based telescopes aimed toward the galactic center. Scientists expect cold planets to be common, so understanding them matters if we want a less biased picture of planetary systems. But a microlensing event typically needs more than 20 days of monitoring. Euclid watched this field for only about 1 day. It was not trying to discover a new event. Instead, it recorded something future discoveries will need, the before frame. NASA Nancy Grace Roman Space Telescope is designed to monitor the same region for planet hunting. Its future observations can catch microlensing events as they happen. When one appears, scientists will be able to return to Euclid's earlier image and ask a second question. Where were the source star and the lens star before they overlapped? Because Euclid separates the stars clearly, their earlier positions can be compared with later Roman observations. The displacement reveals how quickly the stars moved across the sky. Combine that motion with the microlensing light curve, and researchers can confirm the planetary interpretation and estimate the planet's mass. Euclid's mosaic covers the entire region Roman plans to monitor. In other words, Euclid has already photographed the stars involved in future events before anyone knows which stars they will be. One telescope provides the baseline, another records the alignment. The event may last only weeks, but the comparison can span years. This is astrometry used as a time machine. Position becomes motion. Motion sharpens the lens model, and a brief flicker becomes the measured weight of a world we cannot see. Planet hunting is only one use. Because this mosaic is wide, sharp, and time-stamped, astronomers can return to it for studies of binary stars, brown dwarfs, stellar motions, and the distribution of dust across the bulge. The image also preserves the host stars of 2 known cold exoplanets and 51 known planetary systems. As later surveys add new epochs, the scientific value of Euclid's single day can increase rather than fade. That is unusual. Most photographs describe what the sky looked like when the shutter opened. This one also becomes a coordinate system for what the sky will do next. Euclid's range extends far beyond our galaxy. In July 2026, researchers reported 31 of the oldest quasars ever documented in Euclid data. 12 existed within the universe's first 770 million years. 2 formed within the first 670 million. A quasar is the brilliant center of a galaxy where gas and dust spiral into a supermassive black hole and heat to millions of degrees. Finding them so early helps test how the first galaxies and black holes grew. The same mission is therefore working at 2 extremes. Tiny changes between nearby stars can reveal cold planets, while faint ancient light exposes structures born more than 13 billion years ago. The Euclid image is historic because of its scale, but its deeper value is time. Every star has a position. As years pass, position becomes motion, and motion can reveal mass. 60 million suns frozen into one frame. Not a finished portrait, but the first page of discoveries still waiting to happen. The universe is giving us more data than ever. The challenge is learning how to read it.